This video is the first of a series about color vision. In this one we're going to discuss basic concepts about color. In this series we're going to take you on a tour through color vision in 3 steps. In the first 3 videos listed here, we will cover basic concepts about color and color science. This graph about color matching will be of key importance, leading to the creation of this color map called the chromaticity diagram. In later videos we will cover reception of color by the retina and perception of color by the brain. There are 2 ways to talk about color. Technically, color consists of electromagnetic waves from a small region in the spectrum that are detected by the eye and interpreted by the brain. Another way to describe color is to appreciate the richness it adds to our visual perception of the world. Where do colors come from? On one hand, there are colors that nature gives us, the colors seen in the rainbow, which we call the spectral colors. Then there are colors we create by mixing other colors. This can be done by either addition, as with light, or subtraction, as with paint. You need to understand the basics of color in order to understand how color vision works. Let us start with the color white. Is white a color? Technically, yes. It is called an achromatic color, included with gray and black. Understanding how you perceive white is a good place to start in understanding how your perception of color works. Sunlight provides our first and primary source of white light. It was Isaac Newton who, around 1700, began the scientific study of color. Shutting himself in a darkened room, he held a prism in a beam of sunlight. Here is what happened. Sunlight, after passing through the prism, spread out into a rainbow of colors. Using the same simple setup, I got this photo, just like Newton described his result. What an amazing thought! Sunlight, what you would consider as pure white light, contains the full rainbow of colors. If you want to be particular, Newton also recognized it is not the rays of light themselves that are colored, but the perception in our brain. One more point here. If you put another prism in front of the spreading beam, the spectrum would recombine back into white light. The eye is sensitive to a range of wavelengths of light. If only one wavelength is present, like a pure spectral color, then we perceive that. If several wavelengths arrive together, like with sunlight, the visual system adds them together and decides what the resultant color is. Adding lights of different colors together to create a new color is called additive color mixing. Let's take a look at examples of this. Here is a setup on my desk with 3 different colored lights that we can use to make color additions. We can combine 2 colors, for example red and blue, to get magenta. Or we can show all 3 colors, which together add to produce white, seen in the center of the overlapping circles. If I fully overlap the 3 colored lights, we get a full circle of white. Let's explore all of this in more detail. If you have a Windows computer, you have a sweet and versatile little program called Paint. Apple has one like it. By showing you how color mixing in Paint works, you can then experiment on your own, as well as learn a few technical things about color. Mine is from Windows XP, but newer ones are similar. Call up the Paint program. From the top menu bar, choose Colors, then Edit Colors, and Define Custom Colors, and you arrive at the color creator. Concentrating on the right side, the upper box shows a whole color range you can choose from. The lower part allows you to create a technically exact color choice by one of 2 color systems, either specifying hue, saturation, and luminance, or red, green, and blue, called RGB for short. Let's play with that to get a feel for it. In the RGB section, each of the 3 primaries has a range from 0 to 255. First, let's look at one color at a time. In the red box, type 255, with the other 2 boxes left at 0. This shows a fully saturated red color. Then do the same for green and blue. This shows a fully saturated version of each of these colors. Now let's do all 3 colors together. If you set all 3, R, G, and B, to 0, you get black, equals no color. Moving the vertical slider on the right, you will keep the proportions of R, G, and B the same. As you move it up, you will see the color change from black through a range of grays until finally, when they are all at a maximum of 255, red, green, and blue add up to produce white. So far, this is what you might have expected. So now let's do 2 colors at a time and see how this turns out. Before you make a combination, stop and make a guess as to what you think it will turn out. First, what color do you think will result if you add red and blue together? Guessing purple. Close. This is called magenta. What about green and blue? Guessing blue-green. This is called cyan. What about red and green? This is my favorite because I think it's the most unexpected. In additive mixing, red and green together make yellow. If you think the computer is tricking you, here's the same thing done with the lights on my desk. Pretty cool. We have been looking at additive color mixing one step at a time. Here's the same concept illustrated with overlapping circles of color. It's the same as we showed with the 3 projectors, one for each, red, green, and blue. Where they overlap, you have the 2 color combinations. In the center, we have all 3 colors, adding to produce white. A couple of notes here. Primary colors can be any set of 3 colors from which you can create almost all other colors. The only rule is that no 2 primary colors can be used to create the third. One common choice of primary colors is red, green, and blue. Your TV and computer monitor work by this system. By adding these 3 colors together, they are able to produce the range of colors you see on the picture in front of you. Likewise, cyan, magenta, and yellow can be considered a set of primaries, which they are for printers. In this case, they are subtractive primaries. 2 color combinations of these produce red, green, and blue. And when added together, instead of white, they produce a gray achromatic color. Black is usually added separately in color printing. Complementary colors are those that are opposite each other on this color circle. For example, blue and yellow, or red and cyan. One significant property of complementary colors is that when added together, the result is white. For example, here are blue and yellow added together, producing white. The same result occurs with cyan plus red and magenta plus green. This makes sense if you think of the way the complementary colors are created. Yellow came from red plus green, so blue plus yellow is effectively the addition of all 3 primaries. You can do this in the Paint program. Just create the complements as combinations of the primaries. Now, just for fun, you can easily create the additive color diagram yourself in the Paint program. Then go to the menu at the top of the Paint box, select Image, then select Invert Colors, and look what happens. Each of the colors is replaced by its complement, including black for white. I left the names as a reference for comparison. Pretty cool. Additive colors are the result of combining light of different wavelengths. Subtractive colors result from taking specific colors or wavelengths away. This is what happens when light passes through a colored filter or reflects off a painted surface. Let us explore this idea. Here I am showing a beam of white light made up of a combination of red, green, and blue light, just like what happened on my desktop. If you start with a beam of white light and put a red filter in front of it, what is happening? The red filter blocks blue and green, letting only the red light through. A blue filter blocks red and green, letting only blue through. And if you block red and blue, only green gets through. Likewise, you can have a filter that blocks only one color, letting the other 2 go through. For example, if you subtract only green, that leaves red and blue, which we saw before combines to make magenta. Now, can you predict what happens with a filter that blocks only the blue light? It lets green and red through, which add to make yellow. And if you subtract red, what would you get? You are left with blue and green, which combine to make cyan. Paint works along the same line. A pigment in paint absorbs specific wavelengths and reflects the rest. For example, here is a surface painted red. When white light hits the surface, the blue and green wavelengths are absorbed and the red is reflected. Likewise, a paint looks yellow because the pigment absorbs blue light, reflecting both green and red, which your eye senses as yellow. So that is the difference in color creation between addition and subtraction of different wavelengths of light to produce a final color. I've spent a little extra time on this subject because it is a frequent cause of confusion. Now let us talk about ways of describing color. In casual conversation, we can talk about our idea of red, which could be scarlet, vermilion, crimson, maroon, apple red, and so on. But since few people agree on exactly what color each name represents, it's important to have an exact system of color specification. Who needs that? Artists, printers, makers of manufactured goods of all kinds, and engineers who want the display on your computer and TV screens to be as lifelike as possible. There are a number of systems in use. One basic system is the other one shown in the Paint program. It uses three terms: hue, saturation, and luminance. Hue is what you would regularly consider the name of the color, as red, orange, or green. It is specified by a number from 0 to 239. You can watch that change by moving horizontally across the color space. Saturation is the purity or vividness of the color. In this system, the saturation varies as you move vertically in the color space. As you move upward in the diagram, the colors become more saturated. For example, red at 240 is the reddest red. Luminance is roughly equivalent to brightness. You can see that on the scale at the right, like adding white or black to the pure color. Hue, saturation, and luminance is one common system for specifying a color, but there are a number of others. The last subject I want to cover is about the use of three primary colors to match any other color. The concept of color matching is important because this is how your color vision works. Adding together the different input from the three different types of cones in the retina is how you sense colors. Looking at the color spectrum, each of these spectral colors represents a single pure wavelength of light. Each of these spectral colors can be matched using a combination of red, green, and blue light. Let us again use the example of yellow light, wavelength about 580 nanometers. We saw that you could also produce yellow as a combination of red and green. This graph shows how the colors of the spectrum can be matched by using different amounts of the primary colors, blue, green, and red. This graph and the process of color matching will be the subject of our second video. For our immediate purpose, we are showing how a light of 580 nanometers spectral yellow can be matched by using equal amounts of red and green light. Consider this point carefully. By eye, you are not able to tell the difference between the pure spectral yellow and the yellow produced by the combination of red and green. A spectrophotometer could, but you can't. Now, I haven't made an exact match here, but with the right equipment, it could be done. If you took the spectral yellow and shined it through a prism, it would remain the same yellow. But if you shined the combination beam through a prism, it would separate into its component colors. Yet your brain sees each of these as the same yellow. Colors that look the same but have a different spectral composition are called metameric colors. In summary, in this video we aim to introduce the subject of color. We talked about additive and subtractive color creation. Light works by the additive mechanism. For example, sunlight, which appears white, actually contains a full spectrum of colors. Conversely, adding all the colors together produces the perception of white. Paint and colored filters work by subtraction. For example, if a color filter subtracts blue, it leaves red and green, which add to produce yellow. The same thing occurs with pigment in paint. Everything presented here will be of significance when we get to sensing and processing of colored light by the retina. In the next video, we will cover color matching. If you want to read more, here are selected references about color science, and my favorites for general coverage of light, color, and vision.